For the next presentation, we are happy to introduce two mentors from FRC Team 1073, the Force Team. Todd Pack is a mentor for FRC 1073 Team's Software Subgroup, and Claudia Pack is the Software Subgroup Vice President. Their presentation is about OpenMV Custom Vision for FRC, and from my research on this topic, it seems pretty cool. You guys ready?
Yep.
I think we're ready. Can you hear us?
Take it away.
All right, so today we are going to be talking to you guys about the OpenMV cameras. We have a presentation and a couple demos for you.
All
right.
There you go. Let it.
All
You
right.
guys.
Can you see the presentation?
Yep.
All right.
Great, thank you. Sure. So I was going to give a little bit of the intro. So we found these a couple years back, and you know, there's a lot of different ways that people try to use vision or video processing in FRC to make the robots smarter, better autos, and assist their operator. And this just seemed like when we tried it out, and you know, we had some successes and some failures, and we've learned a lot in a couple of years, and we wanted to kind of share that to show what all you could do. So next. You have to, you have to, yeah. Yeah. No.
Sorry.
You have to be there. Click there. There, sure. There you go. Yeah. And so just, we're not, you know, they're not paying us to say this. OpenMV is just a cool open source project. It's something that we found. And so we just like them because of what we were able to learn and do with computer vision using OpenMV cameras. So just to outline of what we'll go over today is a little intro and a basic demo, and then we'll talk about, you know, how do you use this thing in FRC. And then a lot of the work that we've done was how do you make this a robust part of your robot? So we'll go into the sort of tech nitty-gritty of getting this integrated on CAN bus. So it actually ends up being a sort of smart sensor that just runs on 12-volt power and CAN bus, much like a Talon or one of your motor controllers, and talks to the Rio over CAN. That gives you a way to have more than one of these on a robot, and it avoids the bane of our existence. The first couple times we tried to use them, we ended up using USB cables, which just don't survive comp, at least not for 1073 comp. And then we talk about some of the limitations we have and just a little bit of a summary. So what is this thing? It's an open source project. It's called openmv.io. You can go see it online. But basically, it's a small open source machine vision module, and it runs on a 32-bit ARM microcontroller. It's very elegant and simple to program. You program it in a language called MicroPython. So it's really accessible. Very short programs can get a lot done. And there's an integrated development environment that is available on Windows, Mac, and Linux, and we've sort of tried it on all three, so we kind of know that it really works there. It's just a sort of a one-click download, and you have the whole development environment that you need for the camera, so the setup and the accessibility for sort of younger software students or intermediate or even rookie teams looking to try something out is really very high. There's not a lot of separate installation steps and things like that that kind of make it harder to use vision with, you know, other coprocessors. The IDE has just a pile of great examples, like built right into the IDE. You can kind of click an example and it'll take you there and run it. And Claudia is going to show you a demo of that in a second. And then they're fairly readily available. I mean, we've been getting them from the US, but they're available from SparkFun, DigiKey, Seed, and from OpenMV directly, which I think ships them from China. So There's a lot of ways to get them. And then the newest version of the beast is called the H7. And one of the nice things about this camera is that you can swap out the actual imager inside of it. There's a couple of options. One of them is global shutter. So if you have something that's really fast that you want to capture with vision, you might need that. The default option is a color sensor. And then you can swap out all the lenses. So you just go next slide. So another way of looking at it is kind of this. So this is from the OpenMV webpage. So they're about $65 US. So kind of medium priced, right? They're not as expensive as a high-end USB camera. They're more expensive than maybe the minimal Raspberry Pi setup, but they're a lot smaller than that and sort of more integrated. And they have a lot of nice options with tons of I/O. We use the micro USB for programming. It even can take an SD card on the back of it and kind of record what you're doing. Our software VP of last year, Catherine, wrote a little script that let us record what the camera was seeing on a test field for week 0. That's about as far as we got in the season this year. And that let us get a lot of snaps of what the camera really sees during a match to sort of take home and analyze and make our stuff better. So there's a lot of flexibility. Next. And then on the software side, this is a really long slide, but basically you program it in MicroPython. There's a great website, micropython.org, that talks about the language. And then all the special camera stuff is exposed as just a couple of Python objects that look like they're a library in Python for you to use. And all of the image processing is hand coded for the ARM microcontroller. So it's very fast. And unlike that you see with like a USB camera, if you plug a webcam into the Rio or some of those things, it's often difficult to get control of what you want to control in a machine vision sense, where this makes it super easy. You have total control of every sensor parameter like exposure and white balance and all those things that can make your vision go wrong during a competition. You can hard sync with an I/O pin so that you snap exactly when a switch is closed. So it's really gives you low level access to the camera in a way that a lot of sort of other easy to use vision systems, you kind of lose that.
And that isn't to say that it isn't easy to use. You have a lot of control over what it can do. And it's a lot more complicated than just like a camera that you plug in and it gives you feedback and you don't have to write much code. But the code that you write is really easy to learn how to write. Like I learned MicroPython to write this because I had a little experience with Python before I joined the team, but this was like a big thing that I worked on all of my first year on the team. And it was really easy for me to pick up and learn. And within the competition season, I was able to teach other people how to use it. And doing all of the more complicated control, like changing the exposure, setting specific saturation levels if you're using it as a color sensor, and matching it to the environment that it's in. Those are all just really simple, like one line things that you write out, and it really doesn't take much time, and it has a very small learning curve. You learn a little bit and you can do a lot.
All right, so this is Claudia is going to swap our screen share around to show you what it looks like to use the development environment. Yeah.
All right, so here we have, this is just one of their example programs called Find Line Segments, and it follows the same format as almost every single other example program. You import what you need, you have your sensor set up, and then it's just an infinite loop where it searches the frame that it takes for any sort of anything that matches what you're looking for. You can search for blobs, you can look for shapes, you can look for specific colors, you can have edges. There are a ton of really fancy ones where you can just go for specific colored edges or specific like other specifics, but this one is just a line segment. It looks around to everything and just finds line segments that match it. So if we run it real quick, you'll see over here, point it up, that it's finding all the line segments around the areas that match it. And if you go down here, look in the terminal, it looks kind of hectic right now, but if you pause it, you can go back and you can scroll around in it, and it prints out the same thing. It prints out the X coordinates and Y coordinates of each line that it finds, the size of it and the angle of it. And you can change it to print out almost anything you want it to print. And it's super helpful and super useful. We use this for line finding in the 2019 competition season. We had it set to only find lines in white areas so we could track the floor. And you can send back the color of the thing that you're looking for. You just have to program that the specific histogram level is that color. You can send back, you can do some math and send back anything that you want, the length of the line. We created a scoring system to see if the line would be any good or not. One really cool thing that we have is the LAB color spectrum and like color levels over here. The L is the brightness and the A and B are different colors. And you can measure every single color that there is that comes up in this with one of these. If you're doing any sort of color finding and not line finding, you can set the camera to look for something in only a specific range of colors. Like we use this for tracking of field elements. Like this year we developed a power cell tracking program, and in past years we had the cargo tracking, and then even in Power Up, not on this camera, but it was used for a similar thing. We did something where you track the cubes. And it makes the tracking and all of that so much easier, because what you can do is you can pause the program, you can select a specific area. Like if you do that, you can see in this area, it's only displaying the LAB values for that area. And because it's not moving around much, you can see that the levels are very consistent. So if you pause the video, you can go over and you can tweak to find a very specific color of a field element. And it's really, really useful.
And what is in the window, this is all of the code to do this line finding. This is the whole program is like one page. Even though, and you can add more as you go, but it really makes that learning curve really, shallow. So a little bit will get you a lot of stuff going. So
I'm going to swap back over to the presentation.
Yeah.
All right.
All right. So, there's a lot of options for using this in FRC. Basically it's like a smart programmable sort of sensor processor. And I already see a typo now that we're live. Of course, now I can see the typos in our slides. But it can run vision, and that's kind of the fancy thing that it does. But it's also that the blocks of I/O that I showed you on the side of the module, it has a ton of inputs. So digital inputs, a couple of analog inputs. It has I2C, serial, and so it can even read encoders, quadrature encoders. So you could really have like a bunch of sensors come together, maybe out on a mechanism or at the end of a gripper or something, and process it all right there and have a really nice, fast way to debug all that sensing, and then sort of package it up and send something back to the Rio that your command programs could respond to. And so there's a bunch of ways that you can talk to the Rio. You could use any of that I/O to talk to the Rio. You could send back just digital bits. So you could just make an on-off detector with it, or a couple of bits, gives you 4 options. You could talk back to the Rio serial port if you wanted and write your own messages back, but then you only have one of those really built into the Rio unless you use USB serial on the Rio. And we try to stay away from USB. So you could use I2C. That's a little bit range limited. In a competition robot, the Rio tends to be, buried down inside somewhere. And so it's hard to have a long I2C run. you could actually talk back to the Rio using PWM. So the WPI lab has counter classes, and you could take one of your digital inputs and sort of send a number, the pulse width, back. So if you made an OpenMV sensor that was kind of like a range measurement device, you could send that PWM back with a couple of wires to the Rio. And then we sort of picked the sort of general purpose fancy way to do it. You can also talk on CAN bus. So yeah. So there's a bunch of different ways. I think the next slide is, yeah. So this is just a depiction of all the ways, you know, that you could have local sensors that got processed and go through various ways to talk to the Robo Rio. One of the cool ones that we did is there's this thing called the CAN shield. So this is plugs right into the OpenMV camera. And so the CAN shield has some unique properties that make it kind of perfect for what we wanted to do. So it plugs right into the IO pins of the OpenMV, and it gives you a robust regulated 12-volt power supply and CAN transceiver, and it plugs right into the OpenMV camera. So if I grab an OpenMV camera module, this is one with a CAN shield plugged into it. So flip to the next slide. And so that's lets us basically make a module that plugs into CAN and power on a robot, and you don't have to have the USB connections. We use USB for debugging, so you can like run up to your robot in the pits, you can jam a USB cable into the bottom of this to a laptop and like check out the camera and debug it independent of the rest of the system. But the connection is through a really robust DB9 connector with screw downs, and if you make a nice case, that gets you on CAN in a robust way. So, you know, what can you do for it? Well, you know, it's a tiny sensor node, and you know, you can see how big it is, right? It's the size of, you know, maybe a USB camera. There's not a lot of USB cameras this size that allow you to swap the lens out. So this is a big wide angle lens that we have in here. It uses a standard lens called an M12. And so you can buy a ton of low cost lenses, even on like Amazon or somewhere. Here's another lens that's a narrow field of view. So if you need to see far away, you literally just screw the lens out and then screw this lens right back in, right? And you get a totally different field of view. It's like much more flexibility than you get and reasonable cost, right? Those lenses are like $10 or so.
And it's really easy to replace if there are any issues. I remember at one time we ended up with a scratched lens or broken lens or something like that, just from impact and all that.
Impact? What are you talking about?
But in the pits, you're able to just unscrew and rescrew in a different lens. It's also incredibly useful. It makes it a lot more versatile because at times what we wanted to see was a huge picture of right outside of where the robot was. This is when we were using the cameras for video, which we'll talk about later. And then we wanted a couple to see far away, so we knew where we were headed and all that, and it makes it incredibly useful. And the different lenses are better for different things. The faraway lens can help with certain kinds of distance sensing. If you're looking for something to align to, like a target, like the green targets with the reflective tape, those are a lot easier to deal with if you have a far away lens. But if you have a big wide angle, it's a lot better for something that you're tracking on the floor, like any sort of game element, like a power cell, or in past the cargo and all of that.
Cool. And you know, just it has some limitations, but as you saw when we were running the sort of line finder example, it's pretty fast. That example runs with the USB debug cable attached at about 18 frames a second. When you take the USB debugger off, it runs a bit faster. You can often get between 10 and 30 frames a second tracking or updates out of the camera, depending on, you know, your code and how much, you know, resolution you use and things like that.
And it's, once again, it's just very easy to use, and because of its low cost, you can have 1 or 2 OpenMV cameras, you can do anything that a limelight can do, a color sensor can do, a distance sensor can do, pretty much anything you can figure out how to do on an OpenMV camera for very low cost. And it's really helpful, especially if you want a really good, easy to code, robust sensor that will do what you need it to do. The only downside with that is that it does take a good amount of learning to do more complicated things, but it's nothing that's unmanageable.
So this is just a sort of schematic way of looking at OpenMV programs. Almost all of the example programs follow this layout, and most of our programs do too. And basically, it's 4 important pieces. One, you import your libraries and initialize variables. The next step is you initialize the imager, and we usually set gains and exposure or how we want that to work, set up all the stuff with the imager. Initialize any communications. So we'll do that. You do that for CAN bus, or if you wanted to send back a digital output. And then the last bit is the processing loop, which is basically just sort of an infinite loop that runs while you're running. You sample an image. Optionally, you might save something to the SD card. You do your image and sensor processing, and then you sort of talk to your RoboRio with comms at the bottom of the loop. You send your update, whatever update that is. And you might set, there's an onboard LED that you can set so that you can kind of look at the robot, and like a green light can come on the camera if it sees a power cell or something. So you can basically like debug check the thing, hands off, almost like you do when you look at the motor amplifiers and make sure the CAN lights are happy. You can write some of that sort of LED debugging right into your program. That can be very helpful. And then, you might adjust the imager controls in a really advanced application. You might change your exposure or whatever as you needed. And so this is the Fine Line Segments program. So that the top section in red, well, I'll let you do it. You go over it.
Yeah, the top section in red is just setting some parameters. The enable lens core is just a thing to make it so it has more of a filter on it. It doesn't really go in with the sensor setting, but then you import everything that you need. You import your sensor, the image, and the time if you want to have printing FPS, but that's definitely not required. It doesn't need that to function. Then you, in the next darker green section, is all of the sensor settings. Sensor reset just clears anything that it had been previously seeing, or any leftover captures that it has had. It's setting it to the red, green, blue setting, because you can set it to all different kinds. You can have it different saturation levels and a grayscale setting. There are multiple of each. And you set the frame size to the standard one, and then you can skip skip the frames. It's just the amount of frames that you're taking per second. And then you initialize your clock. And then right under that is your while loop. And with that, you take a snapshot, and if it sees any line, or for any line that it sees, it'll draw the line. It's really not complicated, but the output from the lines you can use a lot for, especially if you have a lot of filters on it. You can use this, like we said earlier, for line finding on the floor. It is the most useful, like a line segments program is the most useful for tracking along the floor and aiding in like distance measurement with odometry. It's really cool. And it's really simple and small.
So a couple of just sort of general vision tips and tricks. You capture the images in red, green, blue, right? Those are the sort of color spaces, but usually what you want to do if you're doing any color-based processing, and that happens a lot, I think, in FRC, we use color as a cue to sort of filter out background and noise, right? So the power cells are like this wicked yellow color. People use green lighting to light up the reflector strips, so those are bright green. And so color is how you're segmenting the foreground and background. And it turns out that segmenting colors in red, green, and blue is terrible because there's no fast way to make a threshold in RGB space. If you have lighting and, you know, how when you go to district champs and like they put like spotlights on the field and like strobe disco effects and things like right while you're trying to have your vision work. So there's a lot of lighting contamination and a lot of lighting level changes in competition. And so what you want to use is what they call a perceptual color space, because really what you're trying to find is you separate out the intensity of the light, sort of how much light, from the hue or the color of the light. And so on OpenMV, people use the LAB color space, and you can look that up on Wikipedia, but there's a lot of color spaces that are similar. People will often call it YUV. It's a similar idea where Y is the intensity and UV is the color, if you will. And so we use the OpenMV has a really fast built-in conversion to LAB. And so Claudia in a minute is going to show you using that to make a power cell tracker in the LAB color space. And it makes it really differentiate the color of an object, but the lighting can be brighter or darker by quite a bit, and you still get the same color, which is usually what you want when you're trying to detect a color. You know, the integrated development environment is super helpful, and Claudia talked about it before, but it lets you just sort of plug in the camera, show it an object, draw a box, and capture all the color values that are in that box. And then it lets you tinker, right? You can set all your thresholds and play with it, and you can literally see what the vision system is doing in real time. And it really helps you learn how the vision works, right? You can sort of, every change you make, you can run it almost instantaneously. In a second or two, you can be running a new algorithm or a new idea. And you can get that visual feedback and data feedback in the development environment while you're trying to figure out how you want your detector to work and what you want to filter out and things like that. So it makes it very interactive way to create vision. The sort of the IDE is the brilliant, you know, the runtime is cool and it's what makes it work on the robot, but the IDE is really, I think, what helps you learn about how vision works. And they did a great job with that in the OpenMV team. So
we're going to swap back over to the IDE just a second. All right, so you can see that it still has the frame for new doing the line segment, but if you look up here, we are running a power cell tracking program that we wrote fairly quickly. As you can see, this is the entire program. It's very short, it's very simple, but it runs very well. So if I run it right here, it'll initialize, and if you point it over here, let's see, I just have to scoot this over. You can see that it sees and is putting a box with a little cross in the middle of it to find the center of the blob. You can see that there's a bit of light on top, so it's that color that it is reflecting is outside of what it's supposed to be sensing. And it's fairly robust. As you can see, it's a lot clearer when it's close up, and it kind of goes away when you get far enough away, especially in a weird lighting situation. But it works very well, and you can use all of the data with the little cross thread in the middle. If you return that and then you use it in your actual robot code with some just motor commands, you're able to track and follow a rolling power cell across the field, and it isn't too difficult. And with this, I'm just going to hold it up here and pause for a second. But you see it stays on the frame, and if you select this area here, this is the L value, so it's between like 60 and 75, I'd say, brightness, which fits here, which is our first two colors. It's the minimum and the maximum that the L can be. And then down here you see it's about -20 to 0, which fits within the minimum and maximum, that the A value can be. And then here it's about 40, I'd say, to 70. yeah, about 70, and that is right within here. And you can make these as open or as precise as you want. It is better to have them a little more open, though it does increase the error. If it's too specific of a color, any small lighting change may throw it off just because it'll change all of the values that you're getting. But you can see that it's a really, really simple program. This was based off of their blob tracking example. They have hundreds of examples, and I'd say about 10 of which can help you with blob tracking. They're really great. And you can change the threshold to find any color. You could have it search for legitimately anything that you need. And down here, if you wanted to print out where the little crossheads are, you can in the terminal, and that's what it would be returning. To when we were using Raspberry Pi, it would be returning directly what we were sending out in a print statement. And when you use it over CAN, you have to do a little more funky stuff to make it work properly, to work for FRC CAN. We're going to talk about that a little bit later, but you can really print out anything that you want as long as you have it from the camera with the camera.
Let's change the,
yeah.
the area threshold and the pixel threshold while
Yeah.
we're there.
So
And
like
it should see a little further away.
right here, if you
So
say
cut it down.
it has to be a pixel threshold of 200, it has to take up light space, let's make it 100. And then the area threshold, it can be a lot smaller. This may increase what it's seeing, but it will be able to see the power cell farther away, like it might capture some parts of the wall or the table differently. So if we run it here, I just saved after making those changes, and it should work very similarly. See, it has a little bit more noise, but you can see it all the way back here because this small spot here isn't messed up by the light. And it gets a lot more accurate, once again, when you're not in this crazy overexposed lighting. But the beauty of this is that there are some things you can do. You can set the gain to specific levels, and there are different, like, there's a program in here called like gamma color space or something along that line, where it changes it to reduce the brightness at all times and increase the saturation to specific levels that you can pick. And if you do all of your programming based on those exposure and saturation changes, it'll make it a lot more accurate, even with high exposure like that.
Well, you might want to talk about, so some of that sensor control that we talked about is in there in the initialization. So we turned off auto gain control and we turned off auto white balance because this is a color tracking program. So turn on auto gain, right? You want to leave auto white balance out of it because this is the kind of control that you have. So just, basically change a true to a false. So now it's going to adjust its gain automatically, but not its white balance, right? So you get slightly different imagery, but it still sees the vol. But if we turned on white balance, what would happen is it would change, it'll change the colors that we see on the fly. And if you have auto white balance running, which a lot of USB webcams do, unless you're super careful, it will just, it's a nightmare to get your
tilted up to, like,
your color
if you show it up
tracking.
into light, when it's initializing, everything that it'll see will be white. And if it's tilted into darkness, you will see nothing but darkness because it'll initialize incorrectly and set its auto white balance and the auto gain at the beginning very incorrectly.
So those are the things that you want to have control over in your program. We usually turn them off for color tracking demos.
All right. I'm going to switch back over to our presentation.
All right, so I talked a little bit about the CAN shield before. That's $25 US. So the new OpenMV H7 plus a CAN shield, which is basically a laptop that we're using for debugging to show you the IDE and everything. So that's about $90. So it's still pretty powerful for that. Again, it's more expensive than a Raspberry Pi 3, but it's also a lot smaller. It runs straight off the 12-volt power supply of your robot. So you can literally run a PDP line to this thing. It's got its own regulator. You don't have to come up with 5-volt power, get a stable VRM connection or anything. We had a lot of problems with that with our Raspberry Pis. It's got the CAN bus drivers right in it. and a screw down DB9 connector. So you're pretty much ready to go. So very modular. You can have more than one on the robot when it's on a bus like that. Then you have to write some CAN bus code on your OpenMV. So you can speak FRC CAN, and we'll talk about that. And then you need to write a CAN subsystem in your WPI Lib RoboRio program to listen to what the OpenMV is saying so that you can respond to it in your commands. You basically can define your own interface or API for the messages that you send back. And this year, the WPI Lib docs have a great section that actually, we kind of reverse engineered all this a year ago or so. And we did much better after the docs came out this year because the WPI Lib docs have a section on how CAN works and how FRC CAN works. And we have some stuff that you can look at on our FRC 1073 GitHub pages that will help you out if you want to try this in your own robot or off-season project. So let's flip ahead and we'll walk you through how this works. So FRC CAN bus is kind of a non-standard CAN bus protocol. And since there's only one CAN bus on an FRC robot, you can't just hook up to it and say whatever you want. You have to, conform to how FRC does CAN bus. And so FRC CAN bus uses CAN 2.0 extended frame messages, which are a little bit longer, and you can send up to 8 bytes of data back with every message, and it's about a megabit per second. So under the covers, this is how your Talons, your Falcons, your CAN coders, and Spark Maxes all work in your robots. They talk to the RoboRio using the same CAN protocols. WPI Lib has some CAN classes that help you write a subsystem that speaks FRC CAN. And so we had to figure out how to do this on OpenMV. And so we wrote a little library to do this. There's a couple of sort of tips, pro tips, if you will, for when you're thinking about this. CAN bus messages are sort of best or most robust if they're state messages. So you keep periodically reporting, I see the ball, I see the ball, I see the ball here, or whatever. And the RoboRio kind of listens to that like a heartbeat. If you don't see anything, you don't send a message, and then it knows that there's nothing there, or you said, I don't see a ball, I don't see a ball. As opposed to like an email, which you send and it's guaranteed to be delivered, and you get a response. The CAN bus messages are often just sort of one-way state reporting, and then the Rio decides what's to do about that when it reads the sensor. It's also a great opportunity to learn about sort of real bits and bytes level programming. You are sending bytes. So if you want to send coordinates in an image that's bigger than 255 by 255 pixels, you have to pack that integer into some bytes and then unpack it using bit shifting and masking and things.
It can be really confusing to learn at first, especially if you haven't been programming for your entire life. And it's really helpful to work with a mentor or maybe another student on your team on this part, because it's very easy to have a small typo that really just messes up what you're doing when it comes down to the bits and bytes level of software. But the reward is pretty great because once you figure it out, it's not like it's going to change randomly. There is a specific way that you have to talk to CAN. And once you get it working for your robot and for everything, it's not going to change. So that is the one plus side of all the work.
So next. So FRC CAN bus format. So CAN 2.0 is up at the top of our slide here, and sort of a simplified version of what the frame is. There's a start of frame bit, and in green, there's something CAN calls the arbitration ID, and it's a big long bit string, 29 bits in extended CAN. There's some control bits. Then you get your 8 data bytes that you're actually sending. There's an ACK, a CRC, which stands for cyclic redundancy check, and then an end of frame. The CRC lets all the CAN hardware on the Rio and the OpenMV make sure that there wasn't an error or data corruption on the bus. So you sort of get what you thought you sent. And then the FRC standard is all about what do I put in that arbitration ID. And so the arbitration ID really tells you when there's a message on the bus, who is this message from and what kind of message is it? So for example, depending on the value there, you're going to say, oh, this is the OpenMV sensor number 3 sees a power cell message. And then the data bytes would be, where do you see it? Where is that power cell in the image? And so that's kind of how those fields are used. And the bottom box is from the WPI Live docs, and it shows how they use those 29 bits. So there's a lot of other standards for CAN, like the JEDEC standard for your car and stuff that they use in power equipment. And there's CAN Open that they use in industrial automation. But this is how they do it in FRC. And so there's a bunch of pieces. So flip to the next slide. So you need to pick a CAN bus ID that avoids all the standard ones used on your robot by Talons and Spark Maxes, et cetera. And you need to define your own device type, your manufacturer number, your API class, index, and device numbers to avoid all the standard ones. So to each CAN bus ID that you use in your application, it says this is a specific message about a certain topic from a specific device, that's their device type and manufacturer, and then what's the purpose and meaning of that message, and then which individual device, because you could have more than one. And so you define the content of your message, your 8 bytes, as whatever's getting sent back under that sort of who is this and what am I talking about that's in your CAN bus ID. And so the trick, it was to figure out how to generate those CAN bus IDs that worked with FRC CAN. So next. Oh, sorry, didn't see the slide change. So you're probably going to make what's called a miscellaneous device. And so the documentation defines a device type for that called device 10. You need to avoid all the legal manufacturer numbers that are out there. So you need to be greater than 13 and less than 255. We picked 173 because you can't fit 1073 in 1 byte. And then your API class should follow the conventions of the docs. So like a periodic status message, like I was telling you, hey, I see a power cell or whatever, that would be API class 6. Then you pick whatever indexes you want to whatever you want for your different messages. And the device number starts with 0 for your first device, goes on up to 63 devices. So if I send a periodic status message from our 1073 OpenMV sensor for the number 2 tracker, which is API class 5 index 3, I fill out, I now know what all those bits are in my arbitration ID. And if I pack all that up, it lets me send a legal FRC CAN bus message to the Rio from my OpenMV. And so the OpenMV CAN bus library. So lucky for you guys, we already wrote this and there's a little file called frccan.py. And it's on our team's GitHub site. If you need to contact us, you can contact Team 1073's website, and we can hook you up with that. And we're happy to take questions about it and have people use it. Check out the code, experiment with it in your system. And then likewise, on the robot side, we also have a couple of subsystems that read these messages back from on the Rio. And that's on our team GitHub as well. OpenMV base and OpenMV port tracker .java are all you need to sort of read a CAN bus set of messages from a device. Again, and feel free to contact us on our website about it. So one thing that can be helpful, again, part of the benefit of using the OpenMV is that you could do a lot of vision development without needing a Rio or without needing another coprocessor. So that can help you work in parallel on your team and get different pieces working and checked out before you try to integrate them. If you want to debug CAN messages, one of the things that we've done is we use a BeagleBone Black, which is about $63 in the US from DigiKey, and a comms cape, which is about $35 to make a sort of homebrew CAN debugger. And that'll work with some setup. And it basically makes sure you're actually sending the packets that you think you're sending. And again, it lets you have a sort of $100 CAN debugger that you could use with all of your robot stuff, actually, compared to having to have a Rio before you could test your code. So we're going to hook up something here, and we're not going to do the complete demo, but we're going to do something a little similar. So I'm plugging in a cable that's a DB9, which has a big long cable back to our BeagleBone. You need to run the CAN. It should be up there. So you need to run that guy. All right, and then flip over our screen share to BeagleBone. So the BeagleBone is hooked up to our laptop too. It's just a different window. And yeah, and then go up there and click enter in it. So you'll see, and it's giving us, every time we get a CAN message, we're saying hello OpenMV. And so the first part is that arbitration ID, that's the big long 000065. And then the 8 bytes I'm sending as my payload in my message type 65 is hello OMV. Right. And so that lets you sort of see everything that you're sending right from the camera and debug CAN in a sort of low-tech way that should be, fairly accessible. There's a lot of off-the-shelf CAN sniffers and things. Some of those are weird and require a lot of special software drivers. And if you don't want to get into that, the BeagleBone's pretty easy. Certainly one way to do it. And then this gives you some feel for what the connection looks like. And you don't need the USB connection anymore once you're hooked up with the CAN shield. So pop that off. All right. You can do this one.
So some of the limitations with OpenMV, despite the fact that they're really good cameras for vision processing, is that they're kind of low resolution. If you want to do a lot of just raw video, they don't do great with moving quickly. They don't do great for capturing things far away with complete accuracy, unless you get a really specific lens for that. And as we learned in the 2019 competition season, you can't really get back raw video in any way where it's useful. What we did is we set up a server and we got using like network tables and all kinds of conversion code to get it from the camera to the Raspberry Pi, back to the Rio, back out to the server that was on our driver station laptop. We were giving it frame by frame. It had a lot of room for error. It would mess up a lot. It had really low resolution. It would freeze randomly. And because these cameras aren't really meant to be used as a video camera to look through, we had a lot more success using Jetson Nano and a Raspberry Pi camera and a couple other web cameras. And they worked incredibly well because that's what they're meant to do. They are just meant to record video. And it's also a lot more complicated than it needs to be to get raw video from the OpenMV to any sort of server or back to your driver station, because it takes a lot of code, a lot of weird code. We had to write a bunch of stuff in HTML and it was horrible. And it was really easily breakable. And along with this, all of that server and all of that data relied on a USB cable. The connection on the OpenMV itself is only as good as a USB connection can be, same as the other end that went to the Raspberry Pi, which isn't great because USBs really just aren't the most robust. They're good for desktop working and like any sort of debugging that you have to do while in the pits. But when you're running around in a field slamming into things and other robots, they don't last. What will help with this if you do want to use a Raspberry Pi and a USB is a good case that will hold the USB cable in place. You can just 3D print it, you can CAD it, and it's, if you want to, you can use it as an easy project to teach members on your team how to CAD, something small like a sensor module where it's not super complicated, but it is important to have anyway. And despite all of this, it's really easy to use. It's pretty simple because it's just 12 volt power and then a CAN bus cable, and you can use a lot more than one, and it has very low bandwidth. And another one of the problems with trying to use it for raw video, it used up a lot of bandwidth. We had a lot of problems with that and had to reduce what we were sending greatly to make it meet the bandwidth requirements. But using CAN, you can be about a megabit per second. Yeah.
Well, you can't use all of CAN. You can only use a little of CAN.
I mean, you can only use a little of it, but it really doesn't take that much, which is really nice.
And so, we just wanted to encourage folks to try something new and different. It might, so grab an OpenMV and go through its examples. It is an investment of $65, but that seemed reasonable to us compared to some of the other things out there. You can try it out on your desk. You can try it out with a laptop or a PC very easily, Windows, Mac, or Linux. Learn. It's a great way to learn about how different image processing functions work. There's dozens of them: edge detection, filtering, blurring, color, blob finding, line finding. There's even a module that lets you run small handcrafted neural networks right on the OpenMV camera as a detector. There's face detection, all kinds of crazy stuff. And it is really simple programs that you can understand just by reading them in MicroPython, and you can interact with it really quickly in a very closed loop way. I find that sort of hands-on interaction helps people learn about vision. If you didn't do anything else with it, you might just sort of teach rookies about vision by sitting them down at a laptop with an OpenMV and having them run through some examples. They get a really good feel for what it does, how it fails. They start to understand how things go wrong and what you need to do. Reuse, check out some of the code on our GitHub for interfacing with FRC CAN with an OpenMV, and put sensing out there. That's the #1 thing to get done to make your robot smart. So put a tiny smart sensor, right where you want it in your robot. All it needs is power and CAN cable if you interface the way we did, or maybe power and a digital I/O or PWM cable, and you can get that debugged in parallel while people are building the rest of your robot, without needing the RoboRio or anything. So it gets you a head start on your perception code. And so that is what we have.
Yeah, that's all. Of course, feel free to go to our website, the 1073 website. You can contact our CEOs with any questions that you have, and they will direct it to us. And we'd love to encourage all of you guys to use this, both in off season and in the rest of the season.
Awesome presentation. Thank you very much. I might even get one of those cameras for personal use.
They're pretty cool.
They're really fun.
Yep. We're now going to move on to some Q&A. Priya and Cameron have seen some questions in chat, or they have questions of their own that they want to ask.
All right. Let's see. We have a small list of questions. The first question is, how long does it actually take for a new member to get going with the OpenMV module?
Really not that long. My freshman year on the team, we were looking for someone to do vision processing, and because we had not succeeded as much as we wanted as a team and using some other modules, my dad and I found the OpenMV cameras, and in one meeting kind of sat down, we looked at a couple of the example programs and fooled around with them, and we had stuff that was tracking colors. We had something that was finding lines. It can take about 30 minutes to figure out where everything is, and if you want to do something really complicated, maybe it'll take a couple weeks or maybe a month or so. Depending on the complexity of what you're trying to do, it may take longer. Like, it did take us a while to figure out how to deal with FRC CAN because it's all really low level stuff. But if you're just using it for sensing and you want to do it over a USB cable or something else that's a little less complicated than using the CAN connection, it really does not take that long.
Yeah, I think that's cool that there's different levels of difficulty to it.
Yeah, we had a rookie join this past fall, and I would say in our regular meeting times, probably 2 weeks. I'm thinking Celia got pretty far. So like 4 meetings, and we sort of 4 evening team meetings. We sort of gave her the intro, set her down with one, and gave her something to do. And I would say, about 4 meetings or so, she was getting stuff that worked.
She had a program that we created like a little project for our team to complete last year in the preseason as preparation. And one of the like game elements that we had was this crate with a sign on it that said "Do not enter." It was a white sign with red letters, and she created a program in not that long. And the reason that it took about 4 meetings was just troubleshooting and testing, which is the bane of everyone's existence. But in about a meeting, she had a program using just the blob finding code that could find the big white sign and where each of the letters were, which was really cool.
Another question that we had from the chat was that, have you guys used the OpenMV for any other stuff not related, like outside of robotics? And if so, could you provide some examples?
Well, not on the team. We've just kind of played around with it a bit. We've used it to sense other things. When we were learning about it, we were just using stuff. We used the face detection and was practicing out on both of our faces. And you can really test with anything in your house. If you want to create something that tracks if a door opens, you can have it like find your door. We didn't do this, but you could do it pretty easily. You can have it watch your door, and if the blob around the door changes, you'll know that it's moving. Like, you can do almost anything you want with it. And a lot of what we did do was focused on getting it prepared to use for FRC. But in doing that, we did a lot of little projects from the examples and from other examples that were online, maybe not necessarily provided in the IDE, just to learn how to use it. And it was really fun.
Another question is, do you think this is possible to be an alternative to something like the Limelight camera modules, or is it more of a supplementary vision sensor?
It can, of course, be used in place of a Limelight on our robot for the 2020 season, because there's the big pieces of reflector tape up by the power port. We were actually using that on the top of a turret. We had just a couple LEDs and a camera, an OpenMV camera up there, and a green finding program. It didn't take that long to write. The hardest part was dealing with the FRC CAN, and once we got that figured out, it didn't take that long. And it's very accurate, because if you set the exposure low enough, then it'll pick up the green a lot better. You can turn the exposure up if you're doing any sort of debugging and want to see what the camera's seeing, and it worked very well for us.
But important to remember, so that it's like a Limelight for $100, right? But you can't do it without a really good case, right? So Limelight is a really nicely integrated package with screw down mounts and everything. So this guy, we did solid print. Our MEs had to solid print the case, and we had to integrate our own LEDs. That wasn't that hard, but you do have to do it. And you really need the right mounting. For us, it worked because it kind of integrated right into the way we made the turret this year. So we sort of made the camera mount into the thing.
We worked pretty closely with our members on electromechanical to make sure that we had a case that would fit into the design. We had it CADed, we had it on the robot CAD to make sure there wasn't any problems with where it going to be. We worked with one specific person who was doing a lot of the sensor CADing. And it worked out really well for us to work closely with a couple members of electromechanical on it. And of course, if you wanted to, you could just make a case yourself, print it, and bring it into robotics if your team is okay with it. But I think it's also another good way to practice using CAD, communicating between subgroups, and doing all that.
All right. Thanks to Claudia and Todd for joining us today and introducing us to a cool product.
Thank you for having us.
Yep. We are now going to be handing control of the live stream to FRC Team 1073, the Force team. We at Frog Force were happy to be your hosts for the past few hours, and we wish you a good day. This is Arseny, Cameron, and Priya signing off.